In chapter 19.2, we're going to talk about acid-base titration curves. In last semester, we did a acid-base titration lab, but in that lab, we're only looking for the endpoint of the titration to quantify the concentration of the base. In this chapter, we're going to learn more details about this acid-base titration. An acid-base titration curve is a plot of pH versus the volume of the titrant added. So in this chapter, we're going to look at three types of acid-base titration curves. The first type is strong acid versus strong base. The second type is weak acid versus strong base. And the last is weak base versus strong acid. The figure on the right is an example of the first type of titration curve, which is between strong acid and strong base. So originally you have a certain volume of acid with a certain concentration, and then you start to add the base into the acid. So the base is the titrant. On the y-axis of the plot, you have pH, and on the x-axis, you have the volume of the base added. Because we're adding base, and the base increases the pH of the mixture, as you can see, when the volume of the base added increases, the pH also increases. But notice the way that the pH increases. It doesn't increase linearly, or it doesn't follow a certain pattern. It actually increases slowly at the beginning, then increase rapidly, and then increase slowly again. And this is a feature for the titration curve between a strong acid and strong base. Right? You can obtain this curve by either doing theoretical calculation, which you're gonna get this perfect curve, or you can obtain a curve from experimental data, meaning that you actually perform this experiment and measure the pH as you add different volume of the base, and each of this dot represents a data point. Right, so in the next few slides, we're gonna look into some details about this acid-base titration curve for each type of titration. First, let's look at the titration between a strong acid and a strong base. In this example, we started with 40 ml of 0.1 molar hydrochloric acid, which is a strong acid. And then we start to adding base, which also have the same concentration of the acid. So at the initial point, when there is no sodium hydroxide added, the concentration of the protons is equal to the concentration of the strong acid, because the strong acid will undergo completely dissociation. So at the beginning, without the base, the concentration of the proton is 0.1 molar. Converting that to pH, the starting pH will be equal to 1. So when the volume added is 0, the pH is at 1. So that's the first data point here. And if you look closely at this point, you can see inside your system, all you have is the proton and the chloride. And they both come from the dissociation of the strong acid, the hydrochloric acid. Right, so the initial concentration is equal to the concentration of the acid. That's pretty simple. Now, let's start to add some base into the acid and see what happens. Now let's look at this data point, which represents that 20 ml of the sodium hydroxide of the strong base has been added into the acid. From our data, we know that this pH is equal to 1.48. And let's see how we obtain that pH. So we started by having 40 ml of 0.1 molar hydrochloric acid. So the initial concentration of the acid is 0.1 molar. Right? To convert that into a number of moles, we have 0.004 moles of the proton. And for the base, we add 20 ml of 0.1 molar of sodium hydroxide. So the number of moles of the hydroxide is 0.002 mole. But here I'm talking about the number of moles, not the concentration, because for acid-base neutralization, you want the same number of moles of the proton and the hydroxide. Because the proton and the hydroxide will react and form water, which is a neutralization process. This process can go to 100% completion. So we say the amount of base added is equal to the amount of the proton consumed. So we start with 0.004 moles of proton. Right here, the unit is number of moles, not the concentration. Pay attention to that. So because 0.002 moles of hydroxide has been added, the final concentration of the proton becomes 0.004 minus 0.002. So this is the number of moles of the proton after the base has been added. And for the hydroxide itself, they're all being consumed by the acid, so the final concentration is 0. So after we add 20 ml of 0.1 molar of base, there's only 0.002 mole of the proton left. To calculate pH, we must know the concentration of the proton. So the concentration is equal to the number of moles divided by the volume. So we know the number of moles is 0.002, and for the volume, right, it's no longer 40 ml because we have added another 20 ml of the base. So the total volume is actually 60 ml, which is 0.06 liter. So the final concentration of the proton is 0.033 molar. And to convert that into pH, we got 1.48. And that's how we obtain 1.48 in this table. And if we zoom in on this point, you can see now the system not only has chloride from the acid, which is the spectator ion, it also contains another spectator ion, which is sodium, that comes from the dissociation of sodium hydroxide. Meanwhile, we also have water and a proton. Let's look at this point. This point represents when 40 ml of the sodium hydroxide has been added. This is a very interesting point because it represents the equivalence point. At this point, the number of moles of the proton is equal to the number of moles of hydroxide added. So that is actually the end point of our titration if we have an indicator in our system. To calculate the number of moles, we have 40 ml times 0.1 molar of acid, which is 0.004 moles of proton. And when we add 40 ml of the base, which has a concentration of 0.1 also, the number of moles for the hydroxide is also 0.004. So now we have same number of moles of proton hydroxide, and that's the neutralization point or the endpoint of the titration. So at this point, we call it equivalence point. So the amount of proton introduced from the acid has been neutralized by the amount of the hydroxide introduced by the base. So now, is there any proton left in our system? Yes, because we still have water, and the water can undergo autoionization. So at this situation, the proton concentration will only depend on the autoionization of water. So at room temperature, because the Kw is equal to 10 to the negative 14, which is equal to the proton concentration times the hydroxide concentration. And at this case, because it's neutral, so there's nothing else that reacts with water, so proton concentration is equal to the hydroxide concentration. So both of proton and hydroxide has a concentration of 10 to the negative 7. So by converting the concentration of the proton into pH, the pH is going to be equal to 7. So we say this solution is neutral. If we zoom in, we can still see the same numbers of sodium and the same numbers of chloride, because the amount of each spectator ion introduced at this point are equal. We still have water molecules, and we should have just a little bit amount of proton hydroxide. Because concentration is so low, it's not represented here. Now let's look at what happens if we keep adding the base after the equivalence point has been reached. Because at the equivalence point, all the acid has been consumed. So after that, the pH of the system will only depend on the volume of the actual amount of base added. In your textbook, it gave us the calculation for 50 milliliter of base added, but in the figure, it indicating 60. So to match that, let's fix the figure. Right, so I will say this actually represents when 50 milliliter of base has been added. So I will change that into a 50 also. So the total is 90. Right, so now let's look at how can we calculate the pH when 50 milliliter of the base has been added. So when 50 milliliter of 0.1 molar of sodium hydroxide has been added, the total number of moles of the hydroxide will be 0.005. And then we know that we start with 0.004 moles of proton. So we know that all of the proton has been consumed. So at this point, there's no proton left, which is a wrong statement because we still have the proton from the autoionization of the water, but the amount is so small, so we can assume it's equal to 0. And for the amount of base added, 0.004 moles has been consumed, so we have 0.001 left. So to calculate pH, we need to use we can use the approach of calculating the pOH first, and then use 14 to minus pOH to get a pH. Right, so to calculate pOH, we need the concentration of hydroxide. So for the hydroxide remained, which is 0.001 mole, we can convert that into molar concentration by dividing the number of moles by the total volume. So we have 40 milliliter of the acid solution, adding 50 milliliter of the base, so the total volume is 90 milliliter, which is 0.09 liter. Right, so the final concentration of the hydroxide is 0.01 molar, and convert that into POH, it is 1.95, and we know that pH plus POH should be equal to 14, so the pH is equal to 12.05. So at this pH, we can see that in the system we have chloride from the acid, and we also have sodium, and we have more sodium because we add the base in excess. We still have water, and now we have some hydroxide because the hydroxide concentration is large enough, so we cannot ignore it, right? So we also have hydroxide. Do we still have proton? Yes, the proton concentration is gonna be 10 to the negative 12.05, which is very small number, so we can ignore it. Now we can see that for this strong acid and strong base titration curve, right? So the equivalence point will have a pH of 7, right? And that's only true for strong acid and strong base titration. And then you're gonna see that it's gonna be different if it's involved a weak acid or weak base. So for the pH change over the volume of base added, you can see that the pH initially increase very slow, and then when it's approaching the equivalent point or just past the equivalence point, the change of pH happens very rapidly, and then it slows down again. So this is a feature of a strong acid and strong base titration. And if you turn this upper portion, right, if you rotate this upper portion by 180 degrees, it's gonna overlap with this bottom portion of the curve. Next, let's look at the titration curve between the weak acid and the strong base. In this example, we have 40 ml of 0.1 molar of propanoic acid, which is a weak base, and we are titrating it with the same concentration of sodium hydroxide. Right, so for overall neutralization reaction, we have 1 mole of the acid reacting with 1 mole of base, give you the salt and the water. So for this propanoic acid, it has a pKa of 1.3 times 10 to the negative 5, which is a very small constant. So let's using the same approach as we did in the previous example. So at the initial point, without adding any NaOH, we only have the acid. So the concentration of the acid molecule, HPR for short, is equal to 0.1 molar. However, in this case, because it is a weak base, it won't dissociate 100%, so we have to consider the equilibrium condition. So for this weak acid, when it dissociates in water, it generates small amounts of proton and its conjugated base, and we can express the Ka using this term here. We can then list the ICE table and then make the assumption that the X is going to be small because the small coefficient. So based on this Ka, we can calculate the X value. Notice that the denominator, instead of using 0.1 minus X, we use 0.1 directly. So that's our assumption. By calculating the X is equal to 1.1 times 10 to the negative 3 molar. And remember, you have to compare this number with 0.1 and indicate that the percentage is actually less than 5%, which means our assumption is valid. Then convert the proton concentration into pH, which is 2.96. That means that at the initial concentration with 0.1 molar of this weak acid, the pH is going to be equal to 2.96. So if we zoom in, we see mostly the acid molecule with tiny amount of proton and its conjugated base, and of course water. Now let's start to add strong base sodium hydroxide into this weak acid. First, think about what's gonna happen when the base is added into the weak acid. Are we creating a buffer? The answer is yes. When you add sodium hydroxide into this weak acid, the hydroxide will actually react with the acid and generating the conjugated base of the weak acid. Because the hydroxide comes from a strong base, so this reaction goes to completion. Now we not only have the acid molecule, but also have its conjugated base, because they share a common ion, so we're actually making a buffer in our system. And because we have a buffer in our system, the change of pH is also affected. So if you look at this dashed line here, which represents a strong acid-base titration curve, right, you can see how fast the pH increased, right, until the equivalence point. Now with this buffer effect, the pH increase is gonna be very slow. So how do we calculate the pH of the system during this buffer region? So say we have 20 milliliter of the sodium hydroxide added, right? So when 20 milliliter of sodium hydroxide added, we have 0.002 moles of hydroxide, and the initial amount of the acid is 0.004. Again, because the base hydroxide is gonna completely react with this acid. Right, so after the reaction, you're gonna have 0.004 minus 0.002, which is equal to 0.002 moles of the acid left. And the amount of the conjugated base is also equal to 0.002. So for this buffer, we have the relatively the same concentration of the acid and base. So here the ratio is equal to 1. So using the equation we learned from the previous video, we know that pH of system is going to be equal to the pKa plus the log of the base over acid, and because this ratio is equal to 1, so the pH is equal to pKa plus log 1, and we know log 1 is equal to 0. So the pH is equal to pKa. So that's kind of like in the middle of this buffered region. So at this point, when 20 milliliter of the sodium hydroxide has been added, the corresponding pH is equal to 4.89, And if you take the native log of the Ka value, that's also gonna give you 4.89. Now let's take a look at what happens at the equivalence point. We know that at equivalence point, the amount of the protons equal to the amount of the base. Although we start with a weak acid, but because a weak acid can still react completely with a strong base, we can use the same approach, right, to figure out the equivalence condition. So when the weak acids react with the base, so in this case, the HPR react with the hydroxide. It's a one-sided reaction, so generate is a conjugated base and water. So we want the number of moles for the acid and the base, which is the hydroxide, right? So we want these two components has the same number of moles. So for the acid HPR, the total number of moles, if we multiply them, that's gonna be equal to 0.004 mole. Not molar, moles. Right, so this is 0.004. So that means we also want 0.004 moles of the hydroxide. Right, so by knowing the concentration of this hydroxide, we know that we're gonna need also 40 milliliter of this sodium hydroxide. Right, so that's why the equivalence point happens when 40 milliliter of sodium hydroxide has been added. Right, so in this case, the number of moles of sodium hydroxide is also 0.004 mole. Which also means that the conjugated base, the amount is also 0.004 mole because they have the same coefficient. Right, so everything has a coefficient of 1. We can then convert this number of moles into concentration. Right, so we can use 0.004 mole divided by the total volume. So we have 40 milliliter and add another 40 milliliter, so the total volume become 80 milliliter, which is 0.08 liter. So the final concentration for this conjugated base PR minus is 0.05 molar. Right, so let's say this to equal. Another way you can get this number is just assume that because all the HPR has been converted into PR minus, and the initial concentration for HPR is 0.1, which should be equal to the concentration of PR minus without considering the dilution. But because you have add another 40 milliliter of a base, so you're diluting it, right? So the initial concentration has been diluted by half, so it becomes 0.05. So both ways you can calculate the final concentration of this PR minus. Right, so at this point, all the HPR has been consumed, and all the OH you added also consumed. So all you have is PR minus and water. And this PR minus, which is the conjugated base, right? It's a weak base, so it can react with water, forming a little amount of this HPR again, and the OH. Right, so the pH of the solution of the mixture, it depends on this amount of hydroxide formed. Right, so if we set our ICE table again, this is X, and the PR initial concentration we know is 0.05, and the final concentration will be 0.05 minus X. And again, because this X can be assumed to be very small, so in our calculation, we can use 0.05 directly instead of 0.05 minus X. We know the K value for this acid, right? So we can calculate the Kb, which is Kw divided by Ka. So the Kb of this reaction is 7.7 times 10 to the negative 10, and the Kb is also equal to the concentration terms in this circle here. Right, so these two on those two terms on the denominator, on the numerator is x, right? The denominator is 0.05, so we can calculate x. Right, so that's the hydroxide concentration. Right, so to calculate pH, we first convert the hydroxide concentration into proton concentration using the Kw, and then convert this proton concentration into pH. So at equivalence point, the pH is equal to 8.8. Right, so it's no longer 7, as the case in between the strong acid and strong base. Right, because at the equivalence point, we have PR minus other than water. Right, so this PR minus is a weak base. Right, so that will generate some hydroxide. So the pH is higher than 7, right? So because hydroxide will increase the pH. And if you zoom in, right, so we have this conjugated base, right, and water molecules, and also a little bit amount of hydroxide. And this little one is sodium, right? This is sodium. After the equivalence point has been reached, the pH of the system will only depend on the actual amount of the strong base added. So the curve has the same shape as you have in the previous example, which is between the strong acid and strong base. You may argue that, well, how about the existence of the PR minus or the conjugated base of the weak acid? Well, it does exist, but again, it's a very strong base. It's a very weak base, right, compared to the sodium hydroxide added. Right, although that's gonna affect the pH slightly, but once you add more sodium hydroxide, it's much stronger than that PR minus. So that won't affect the shape of the curve. So you notice that the dashed line here start to overlap with the solid line. Right, so the way to calculate the pH is exactly the same as we did in the previous example. Last, let's take a look at the titration curve between a weak base and a strong acid. As you can see from the figure on the right, it's very similar to the one that we see earlier between a weak acid and strong base, but it's the opposite direction. So the pH is dropping in this case because we are adding the acid into the strong acid into the weak base. Right, so at the initial point, right, we start with a 40 milliliter of 0.1 molar ammonia, which is the weak base. Right, so this weak base has it's a conjugate acid, right, has a pKa of 9.25, so the Ka is 10 to the negative 9.25. Right, so the initial pH is totally depend on the concentration of the ammonia present, which is 0.1 molar. And the ammonia can generate a little bit hydroxide, so that's why pH is above 7. So using the same approach, we can use the expression for Kb. So Kb can be calculated by Kw divided by Ka. Right, so Ka is given. Right, so first we can calculate Kb, and using the Kb value and this expression, calculate the x the hydroxide generated. Right, so after we get the x, which is the hydroxide concentration, we can convert that into proton concentration using Kw, and then convert the proton concentration into pH. Right, so with 0.1 molar of ammonia in 40 milliliter of solution, the starting pH is about 11. Right, so if you zoom in, you only see ammonia and water. So in this figure here, water molecules are not shown, right? But you should know water also present. And also we have some hydroxide, right? Because the amount is not very high, so it's not shown here. So when we start to add the strong acid HCl, So again, we're creating a buffer, right? Because the ammonia will react with HCl and generating this ammonia chloride. This is an ionic compound, right? So actually it is NH4 minus, NH4 plus, right? The ammonium ion and the chloride ion, and the chloride ion is the spectator ion, right? So now you not only have ammonia but also have this ammonium ion, so you generate a buffer. So very similar to the titration between the weak acid and strong base, right? So you have this buffered region. So in the middle is where we add 20 milliliter of the hydrochloric acid, right? So at that case, you have half of the initial ammonia converted to ammonium. So you have a 1-to-1 ratio for these two components in the buffer, right? So this log 1 equal to 0, right? So this is log 1 equal to 0. So the pH is equal to pKa, and the pKa is 9.25, right? So when 20 milliliter of the hydrochloric acid is added, the pH is 9.25, right? So it's the same approach as we see in the previous example. At the equivalence point, again, we want the same number of moles of the proton and the hydroxide, right? So in this case, because ammonia will completely react with the hydrochloric acid, because hydrochloric acid is a strong acid, right? So the amount of proton from the hydrochloric acid should be equal to the base generated from ammonia, right? So because ammonia, right, when ammonia reacts with water, it generates hydroxide and ammonium. So using the same approach, we said that so the number of moles for the ammonia at the beginning is 0.004, right? So it's 0.004 moles, right? So by letting it react with the strong acid, the ammonium ion generated is also 0.004 mole, right? So the amount of the acid consumed is also 0.004 mole. And with the concentration of the acid it being equal to 0.1, that means 40 milliliter of the 40 milliliter of the acid should be added, right? So the equivalence points happen at 40 milliliter. So at this point, all the ammonia has been converted to ammonium, NH4 plus, right? So again, we should separate this ammonium chloride, right? So all the ammonia has been converted to ammonium. So this ammonium concentration is equal to 0.004 mole over the total volume, which is 40 plus 40 milliliter is 80. 80 milliliter is 0.08 liter, right? So the concentration is 0.005. And again, you can use the dilution factor, right, to calculate it. You're gonna get the same result. So at the equivalence point, the pH only contribute to the amount of proton generated from ammonium, right? So we just calculate the concentration of the ammonium ion, which is 0.005. So using its Ka value, we can set the this equal to x. Right, so calculate x. That's the proton concentration, and convert that into pH. So after you calculate x, x should be equal to 10 to the negative 5.27. Right, so the pH will be equal to 5.27. As you can see, at the equivalence point, it is the pH lower than 7, right? So it is a little bit acidic, and that is because the ammonium ion is the conjugated acid of the base ammonia, right? So that will generate some proton. So after the equivalence point has been reached, we have the same deal. The pH will be only affected by the amount of the strong acid added. Right. So again, although the ammonium exists in the system, could also generate proton, but it's so weak compared to hydrochloric acid. Right. So we say the proton concentration only come from the addition of the actual amount of the acid, which will affect the pH. So the shape is the same as the one in the strong acid and strong base curve. So to monitor the change of pH during a acid-base titration, we should use something called a pH indicator. A pH indicator is a chemical that changes color when the pH changes over a certain range. So last semester when we did the acid-base titration, we did a strong acid, strong base. So remember we picked this indicator called phenolphthalein. So we add base into acid, right? So when the endpoint reaches it, the color become pink, right? So it starts with colorless and become pink. So in this chart, you can see the color of different pH indicators, right? So this is the range of pH, right? So for example, if we look at methyl red, right, that means for this indicator, when the pH is below 4, it appears to be red, but after maybe 6, right, so it become yellow. And some pH indicators have more than 2 colors. I have 2 ranges. For example, this thymo blue and this alizarin, right? So you see they have 2 stripes, right, when the pH changes. Right, so now let's think about how can we pick, right, or what should we base on when we pick the pH indicator. And as you can see, think of that you should think about the endpoint, right? So what's the pH of the endpoint, and you want that this color change pH be close to that endpoint pH. For example, this is the strong acid and strong base titration, right? So that's what we did in the lab. We choose phenolphthalein as a pH indicator. And notice that for this pH indicator, right, so it is colorless, right? It's colorless when the pH is below 8, and it is pink, right, when the pH is above 8, right? So it's a pink when the pH is above 8. But actually, did you notice that this pH 8 is not like equal to or close to the endpoint of a strong acid, strong base titration, which is pH equal to 7. But it still works. And the reason is that this titration curve, right, this vertical region here, right, this vertical region here that covers this pH change, the change of pH, right? So at pH 8, phenolphthalein changes color, and although it is 1 pH unit away from the endpoint pH for a strong acid and a strong base titration, but because it's in this vertical region, by just adding one extra drop of base or acid, the color is gonna change, right? So for example, if we add the base into the acid, although the endpoint happens at pH 7, but by just adding one drop of base, the pH gonna goes up, right, rapidly, which is gonna cover that region, which is pH equal to 8. So that's why the phenolphthalein works. Also, if we add acid into a base, right, so although the endpoints at pH 7 and the color should not change, but for methyl red to change color, the pH should be below 6, right? So from 6 to 4, it changes color from yellow to red. And by just adding one more drop of the acid after the endpoint, you can see that will cover this color change region. So methyl red will also work if we add the acid into the base. Right, so now we should be careful about the equivalence point and the end point of the titration, right? So they're actually not the same point. Equivalence point is the point when you have the same number of moles of a proton on the hydroxide. But for the end point in the titration, it is the point where you observe this color change, right? So it might be slightly different than the equivalence point. So now let me ask you guys, which indicator would you choose for these two titrations? First, you have a weak acid and a strong base, and the second, you have a weak base and a strong acid. Right, so the choice is between phenolphthalein or methyl red. Right, so comment below and let me know what do you think. So for B, what you choose, and for C, what you choose. I will go over the answer in the next video. For homework, you're gonna work on calculating the pH during a titration between a strong acid and strong base. Right, so I'll see you guys in the next video.